Mhm. All right, is everybody looking at my PowerPoint presentation?
Yes.
Perfect. Let's do the element of the day. So, hydrogen is the element that naturally fell out of the Big Bang. And here I'm talking about the Big Bang in the context of before stars were ever formed, before the universe itself was basically just a gigantic star. I'm talking about when the universe was so small that it was basically so energetic that every time matter started to form, it was just blasted into pieces. A proton, for example, is born out of three different quarks. It's impossible for quarks to join together under that kind of temperature. So we had nothing that we would recognize as normal matter. When the universe cooled to the point that everything made out of matter wasn't blasted to pieces immediately, we got a whole bunch of hydrogen. And that hydrogen is what falls out of pure energy when it has an opportunity to form matter. I'm super oversimplifying the situation, but that's all right. This is a general astronomy course. Now, one thing that this slide doesn't talk about is that cosmologists, who are the people who deal with the formation and end of the universe, and physicists just in general, have a really hard time explaining why there isn't more or less antimatter than there is regular matter in the universe. All of the equations that deal with this, which we will not touch at all, suggest that matter and antimatter should have been created in equal quantities. If that were true, then hydrogen and antihydrogen both would have fallen out of the high energy soup in the early universe, and all the antihydrogen would have found all the hydrogen and made photons, and that would be all the universe was made out of today. So, why didn't that happen? I have no idea, and neither does anybody else. Oh. So, stars specialize in turning hydrogen into other elements, and even given that stars have been merrily churning along, turning hydrogen into other things, the stars are really the only thing nowadays that turn hydrogen into any other thing, it still is most of the elements by count and also most of the mass in the universe. So we're not running out of hydrogen. But in order for hydrogen to form a star, it has to be involved in a particular type of shock wave at a particular type of temperature. And looking out over the whole universe and analyzing the different sorts of galaxies we see and stuff like that, astronomers have concluded that most of the stars that will be born in the universe have been born. We have reached peak stars, the same way sometimes people talk about reaching peak gasoline, where most of the gasoline that's in the planet of the Earth has been extracted and is used currently. So I'm definitely not saying no more stars. And if you remember, M dwarfs lived for 500 billion years or so. Oh, sorry, 100 billion years or so. And the universe itself is only 14 to 70-ish billion years old, depending on whatever our current calculations are. This is being translated as 14 to 70-ish, but I mean to say 14 to 17-ish billion years old. So there's stars that are going to take many times the current age of the universe to die, and more of those stars will be born in the future. So the story is far from over, but nonetheless, we expect that most of the stars that are going to exist either have lived and died already, or else are currently existing. Today, we're going to talk about the tools of the astronomer. That's all we're going to be focusing on, which is why we're going to be circling back through so much about light and how we do observations with light, because this is going to be all about how different types of telescopes work. And telescopes work with light, and not just visible light. Remember, there's tons of radio telescopes scattered all over the Earth, tons of visible telescopes scattered all over the Earth, and we have gamma ray, X ray, ultraviolet, infrared, and microwave telescopes in orbit around us. Actually, we don't currently have an infrared telescope in orbit around us, but all the rest of the wavelengths are represented. So remember, this has been going on for a while. Machu Picchu was a pleasure palace for the Incan royalty, but it was also, we're pretty sure, an observatory. I say we're pretty sure because when the Spaniards came to what is present day Peru/Chile, they didn't leave a lot behind to tell us what was actually going on with that culture. And then Stonehenge is clearly a astronomy calendar meant to tell you when equinoxes and the solstices were happening and who knows what else they had in mind when they built it. And this kind of stone calendar was scattered all over northern Africa, Europe, Western Asia. It was not a new idea. It was created many, many, many places. It's just Stonehenge is the largest and the best well known of the ones we're familiar with. So people have been trying to figure out astronomy for a while. We've just been getting better and better and better at it. Speaking of which, happy equinox. Now that this has occurred, keep an eye on the full moon. Once the moon is completely full, the next Sunday will be Easter. Remember, Easter is always the first Sunday after the first full moon of spring. So, working on a telescope, people invented the idea of shaping glasses so as to magnify things and or help people with their vision sometime around 1200 Common Era. And these are mainly used as reading glasses, which magnify. Very important as you get older. I have them. And thus the manufacturing of glass lenses began. Telescopes were first invented in the 1600s, which was hundreds of years later. It took a while for people to figure out that they could put one lens in front of another. Galileo commonly gets the credit for the invention of telescopes, but he did not make telescopes first. All he did was make them way, way, way better. The telescopes greatly increased the number of faint objects visible. Remember that when Galileo pointed his telescope at that weird band of light that crosses the night sky if you're in dark skies, that he was able to see that the Milky Way, that band of light, was lit up because it was comprised of many, many, many stars that were too far away for us to distinguish them as individual stars. They aid in the magnification of objects, so Galileo was able to look at the moon and see the shadows of craters for the first time. He was able to look at Venus and see the phases that Venus was in for the first time. And they greatly increased the angular resolution of objects. Now, everything Galileo was looking at was sufficiently far away that increasing the angular resolution was not actually all that useful. You know, a dot looks like a dot unless you're able to increase the angular resolution by a lot. But modern telescopes can do that. If I was able to meet y'all in person, one thing I would absolutely do is show you the rings of Saturn, which actually Galileo was able to see. One thing I would absolutely show you is the bands of color that are on Jupiter, corresponding to the storms that are currently raging on the planet. And I would absolutely show you the polar ice caps of Mars, because all these objects are up in the night sky nowadays. However, every semester of the pandemic, I have asked the Napa Valley College administration if it's possible for me to meet my astronomy students in a socially distant context and wipe down the telescope with alcohol wipes in between every use, and the answer is still no. So, sorry, I will make the same promise to you that I've made to every other class before, which is that when I finally get an opportunity to have an observation day, I will flip back through the previous classes on Canvas, and I'll let you know what day that will be. I don't expect to get too many participants, but those of you who would like to join will be able to join, and I will show you whatever is up in the night sky then. Mars moves around pretty quick, so who knows if it'll still be visible, but Jupiter and Saturn move very slowly, and so I expect that they will still be around.
Cool.
So, This is what glasses do for you. If you're farsighted, you need converging lenses, which were made a bit later. If you're nearsighted, you need diverging lenses. You need these because of a mild deformation of the eye and or damage or fatigue to the eye. One thing I was told growing up is that if you read all the time, you will ruin your vision. Turns out that's true. People that read all the time tend to become more than a little bit nearsighted, which is probably a big part of the reason that there's so many nearsighted people in our society. I would argue that that is a good trade-off. If you're advising young children on this, there are things you can do to diminish the effect. Taking frequent breaks from books and focusing on the horizon seems to be able to mildly diminish the effect, but even so, if you read a ton, there's a very good chance you're going to end up nearsighted. So here is a little bit of the internal architecture of an eye. So this is what the lens inside of your eye should be doing, give or take. It should take light that's entering the pupil and focus it on what's called the fovea, on the most neural dense part of the eye. So that's what you want. Pardon me, I can't seem to get this to play. Now, a nearsighted eye will focus light before the foveal. Now, I can't see how the rays are crossing, so where they all cross is the focal point. So I can't speak perfectly to the biology of this, but the lens inside of your eye is deformable. This much I know for sure. There's muscles all around it, and they can pull on it to make it thinner, or they can relax to let it go back to its thicker state. And the reasoning behind reading a lot kind of hurting your vision is that if you read a lot, the muscles will not get as much exercise as they would, and your eye is not as skilled at deformation as it might be otherwise, and consequently you end up nearsighted. And so, that can be corrected with a diverging lens, by a lens that makes the rays of light bend away from the way they were traveling earlier. This also means that you can't use a nearsighted person's glasses to start a fire. So if you're ever lost in the wilderness, you're taking a survey of the people that are lost in the wilderness with you, they're all nearsighted, no point in picking up their glasses and pointing them towards a campfire while the sun's up. It won't do you one bit of good. So nearsighted people are very good at seeing things that are nearby and poor at focusing on objects that are at a great distance. Farsighted people have the reverse problem. They're good at seeing things at a great distance, but poor at focusing at things that are nearby. And it is far, far, far rarer than being nearsighted. But being farsighted is corrected by a kind of lens we call a converging lens. And because they make rays bend towards each other more strongly, they can be used to start a campfire. And that is to some extent of the full extent of what I know about our most valuable visual instrument, which is the eye. I mean, I'm a physicist, not a biologist. Feel free to ask me any follow-up questions, but I probably won't know the answers. So lenses work by something called refraction. And you see a lot of examples of refraction in your day-to-day life. Here's the upshot of how it works. When light goes from one medium to another medium where it has really different properties, usually the density of the medium will change a lot. Like, for example, you're going from air to water. Then the light will bend. and a few other things will happen, but for our purposes, it's mainly important the light will bend. So you can see this by taking a clear glass of water and sticking a pencil or something into it. You see it when you're under a perfectly still swimming pool, if you can actually find such a thing, and looking up at the things that are around the swimming pool and noticing the distortion. You can see this by climbing on top of an aquarium and looking at fish at a great angle, and then moving your head until you're dead on top of them and comparing their size to what they. So examples of refraction abound in this world. And lenses work by refraction. They're made out of glass. Glass is a distinctly different substance than air. And so when light enters the glass, the light will bend. Like that. And so when astronomers are using refraction to create magnified images, that means they're using lenses made out of glass, usually super expensive glass because astronomy. There's one other way to make light curve, and that is using really very large amounts of gravity. But we'll get to that in our relativity section. For those of you who want to read ahead, this effect comes out of general relativity, not special relativity. We will talk briefly about both, though. So if you want to form an image, you take a lens, you shine light through it. If the object is really, really, really far away, then the light will be almost parallel, and the light will all converge at a very sharp point called the focal point. Now, because light travels at different bending angles for different colors, often that focal point is a little different for red than it is for blue, than it is for green, and this drives astronomers crazy, but there are ways to adapt for it. Let me take a moment. Let's go to the whiteboard. I want to show you why light from a very distant object is going to be almost nearly parallel. So is everybody focused on the whiteboard right now? I will take your utter silence as a yes. And I also notice that the screen has become completely blurry again. I'm going to unplug the camera and plug it back in. Are we recording? Yes. I assume we are recording. Yes, we are recording. I see pause recording and stop recording, not start recording. Hold on.
Oh, sorry. I put that in earlier.
No worries. I will be back with you in but a moment. All right. Say something if you're hearing me, okay?
Yep.
Appreciate it. All right. So here's a star. This star is much closer than any star reasonably is, and thank goodness, because we'd be dead. And here's a telescope, which is much bigger than any other telescope would be, which thank goodness, because otherwise it would cause the Earth to swivel off its axis. And so stars shoot out light in all directions. But notice that most of this light, all the light that I've drawn up to this point, is not going to intercept the telescope. So there's countless rays of light that come out of a star. I'm just going to create a few more. And the only rays of light that can make it through the telescope aperture, through the first lens of the telescope, are rays that are more or less headed straight for it. That means that they're very, very, very close to parallel. And in this case, I've drawn a star that's super close. As you might imagine, when a star gets to be at regular star distance, the light has to be very, very, very parallel. I notice that we're a bit off focus again, but any questions or anybody want me to unplug and replug the camera, or is that adequate? All right, back to this then. So let's look at some examples of refraction. So right now, this is demonstrating something I'll show in a little bit, which is reflection. That's how mirrors work, but every time you have a change in surface, a little bit of light always reflects, and often some light makes it through. And when the light does make it through, as it's about to, notice that the direction of light changes by quite a bit. This is refraction being demonstrated. This is what actually happens when you go from a medium like water to a medium like air. In this case, water is on the bottom and air is on the top. And incidentally, this is no part of the class, but just for the sake of fun, what you're seeing now is an effect called total internal reflection. And that is a special angle at which, if you have something like water or fiber optics that are surrounded by air, there are certain ranges of angles at which the light does not refract at all, and it only reflects. And this means that you can make cables of basically arbitrary length, and there's no signal loss within them whatsoever. When we imagine how the internet works, I think the vast majority of us think that probably signals are collected from our cell phones' radio emissions and sent to a tower, or from our Ethernet ports and sent to via wire to a tower, and then rays of light beam upwards into the sky, strike a satellite, and then fall back down on a receiver in some other continent. That's not how it works. 95% of what we think of the internet that travels in between continents works via fiber optic cables that are just lying on the ocean bottom. If you look up where they are, you can walk up and down the coast of California. You can see these thick, thick cables go into the ocean. And then if you look up where they are, you can take a boat trip to Japan or Malaysia or Australia or whatever and see these big, big cables rise up out of the ocean. And then, oh, sorry, does somebody have a question?
No, sorry. I forgot to mute myself.
No worries. Are you still looking at my Firefox? Are you still looking at my web browser, I should say?
No, I don't think so.
Okay, well, then let's get
Oh.
back.
No, I see it.
And then I wanted to offer this up as a challenge to the course. Can you figure out what is happening here? You may not see it well unless you're in a pretty dark room, but what is essentially occurring is light is being shown in, and then it's curving, and it strikes the bottom again, and then it bounces up, and it curves again, and it strikes the bottom, and it bounces up, and it curves again. All right, I gave a count of 5 in my head, so unless somebody really wants to jump in, I'll give the explanation. Back to the whiteboard. Or not. Hold on. Sorry, I've been doing this for long enough that it should be impossible for me to be in this situation, but I can't actually. Oh, all right. Back to the whiteboard. Now that I need it again, I'll unplug the camera and plug it back in. So what you're seeing is the quality of the air changing. And because the quality of the air is changing, the light has this capacity to bend over and over again. And you've seen this, or at least if you've ever lived in the Southwest, you've seen it. And you see it when there is a pleasant blue sky in front of you, endless asphalt on the road. So you should be seeing just black all the way to the horizon. But instead, a portion of the road seems to have a bluish color, as if there's water there, or as if the sky is contained within the road itself. Indeed, there is not water in the road. It's just that the light from the sky is doing the exact same thing. In this case, the quality of the air changes because it is super hot down here and cooler up here. And that's what gives the light the capacity to constantly bend and bounce and then constantly bend again. In the case of the water solution I showed you, it's a bit trickier. What I did was I dumped a sugar solution into it, and then I waited a few days for it to settle. It's highly concentrated sugar on the bottom, and then every centimeter up from that, it is less and less and less concentrated. So that is refraction. And here is how a refracting telescope can be set up. You have a lens. That lens creates an image at a certain focal point. And then you've got the image captured. It's there, but it's not magnified at all. And then another star can be imaged by the lens, and the image will show up in a slightly different location because the star's light started from a slightly different location. And you have two stars next to each other, and you'd like to compare them. And this is how you do it. You need a secondary lens to act as your eyepiece. And hold on a second. When I say a secondary lens, I mean this. I mean a magnifying glass of exactly the sort that Sherlock Holmes uses. So you get the image in one spot here, and then you use the magnifying glass to look at the image until the magnifying glass enlarges the image. Telescopes aren't any more complicated than that. You use one lens to put the image there, and then you use the magnifying glass to peer at the image and make it bigger. Just like you could use any magnifying glass to expand anything. And I'm going to try this, but I won't be able to see it because I have to look directly at the camera. Did you see my eye as being highly magnified at any point in there?
Yes.
Okay, well, that's how magnifying glasses work. So in this case, my eye is representing the two stars in some focal plane that I can resolve. And then I just use a magnifying glass to blow up the image of those stars, because you would like the stars to be bigger. Microscopes work the exact same way. You pretty much use one lens to put the image where you want it, and the second lens is only acting as a magnifying glass. The name for the first lens is called the objective lens, and the secondary lens is called the eyepiece. You want your objective lens to be big for a couple of different reasons. I'll get to reason number 2 in a little bit, but reason number 1 is just that the lenses are basically acting like a bucket. The bigger the bucket, the more light the lens can collect. So a question for you, which you don't have to answer actively. Is this a length effect, an area effect, or a volume effect? You don't have to answer it actively, but you're welcome to if you wish. And the answer is that the aperture, the primary lens, is just a circle. And the amount of light it can collect is the area of that circle. I'll step off screen to make sure everything is in frame. Great. So at the beginning of next class, I'm going to put you through a bunch of length, area, volume comparisons. So I'm not going to make you practice this too much on your own, but let me give you a few examples. Let's say you're comparing a telescope that is 1 inch in diameter to a telescope that is 4 inches in diameter. Make a ratio, as always. 4 divided by 1 is 4. It's an area thing. Area is a two-dimensional thing, length and width. So the amount of light that is collected is 16x more. Say you're using a telescope that's 2 inches in diameter, and you go to a telescope that is 18 inches in diameter. Make a ratio. And 18 divided by 2 is 9. 9 times 9 is 81. The amount of light you're collecting is 81 times more. And that means you can see objects that are 81 times fainter than the objects you can see that have a diameter that's 2 inches. So now let's compare the size of a human pupil, which is about 0.05 inches, to some of the biggest telescopes of the world, which would be, hold on, I'm doing some math in my head real quick. Okay, about 2,500 inches. So now I'm going to make a ratio. I would like to reach for my calculator, but I don't have one. So 2,500 divided by 0.05. So the ratio is 50,000. And the amount of light you can collect that's more is 1, 2, 3, 4, 1, 2, 3, 4, 2, 5. So when you compare a modern telescope to the human eye, a modern telescope can collect 2,500,000,000 times more light than the human eye can collect. That means, and by modern telescope, I mean research telescope, not the sort that you can buy for your backyard. Those only cost about the price of a car, a used car. A modern research telescope will run you anywhere between a few $1,000,000 to a few $1,000,000,000. But anyway, a modern research telescope can see objects that are 2,500,000,000 times fainter than your eye can see. So that's a substantial difference. This is the main way we know about how much light very, very, very distant galaxies emit, because we've magnified our capacity to detect light by that much. As always, if there are questions, hit period enter so I know something's coming up. So here's our largest refraction telescope in the world. It's 1 meter long, which is pardon me while I do a conversion between yards and meters. 96 inches, I say, without a lot of confidence, I think. I really don't think at all in terms of imperial units anymore. So that's pretty big, but it's not at all as big as the biggest research telescopes used today, which could be like 64 meters or some such. And that's because there's real problems with refraction telescopes. The main problem is that the primary lens, the first lens that light enters through, is going to be really, really, really heavy. If you make a lens that is 1 meter wide, 1 meter being about the same thing as 1 yard, then you've made a lens that is about as wide as from your fingertip to your left shoulder. And after you refine all that glass and shape it into the kind of lens that you need, you have an extremely heavy objects that you're dealing with. And that will make the tube sag. It makes it hard to swing the tube around. You've got to have counterweights to keep the whole thing from just having the side with the objective fall to the ground immediately, so on and so forth. It's just not ideal. Also, you have chromatic aberration. Recall that a prism can take white light and split it into a rainbow. And if you're wondering what that looks like, and you're a fan of 70s rock, then picture the cover of The Dark Side of the Moon, in which a beam of light has exactly that happening to it. So light of different colors bends by different amounts in a lens. And that's an issue, because rather than having the blue, the green, and the red all nicely lined up where you could use one magnifying glass to get the sharpest possible image, they're all in slightly different spots, and you have to move your magnifying glass around to get the sharpest blue image, the sharpest green image, and the sharpest red image. And that's a big headache. So there's the planet Jupiter with chromatic aberration, and there's the planet Jupiter with no chromatic aberration. Incidentally, if your glasses are thick enough, you will see chromatic aberration all the time. So every time I look at the moon, there's a blue side to the moon and there's a red side to the moon. I don't know how many of you are in the same boat, but if you experience this, you are not crazy. Because you are wearing glasses, there really is a blue side to the moon and a red side to the moon, due to chromatic aberration that's occurring inside of the glasses due to the blue light and the red light bending by slightly different amounts. And you end up with more red light on one side of the moon and more blue light on the other side of the moon. And the effect's really there. It's not just in your imagination. My glasses are so strong that I see chromatic aberration when I look at white text on my cell phone. Hopefully none of y'all are in that boat. But if you are, feel free to turn on your mic and share your anecdotes. Refraction is also how rainbows happen. Although in the case of rainbows, you have to deal with a wee bit of reflection too, because the light has to travel through the rain droplet. The red light travels differently than the violet or the purple light does, but it needs to reflect off the back of the water droplet in order to come back at your eye. Completely understanding this will make it much easier for you to create a rainbow using a garden hose in your backyard and thus impress people. Stand with the sun as close to directly behind your head as possible, and then spray the water in front of you with your eyes focused as near to opposite the sun as they possibly can. And you'll see two different rainbows, or at least you should. So we've already gone over the types of light. I still want to give you 1 minute to do this. I want you to write down every kind of light you can think of in order from highest energy to lowest energy. This is the kind of thing that I'll test on a quiz. I'd like you to have it memorized. Of course, you're not anymore taking quizzes in class with me watching you like a hawk, so you may not immediately see the point of this, but it's still an important thing to learn for the class. And go. If you finish this, then write down the visible light in energy from the highest energy light you can think of to the lowest energy light you can think of. But what I'd like you to do first is write down the whole electromagnetic spectrum. starting from highest energy to lowest energy. And I'll even get you started. The highest energy kind of light is gamma rays. Anybody need more time? Is everybody looking at the whiteboard? So silence gives assent, I suppose. Obviously, you're not going to talk to your neighbor and mention things you know about each type of light. So I'll just run through them for you. You have gamma ray light, X-ray light, ultraviolet light, and the least energetic kind of ultraviolet light will make it a little bit through Earth's atmosphere, and that's why we get skin cancer. Visible light, infrared light, microwave light, and finally, radio light. And then for most energetic type of visible light to least energetic, I have violet, indigo, blue, Roy G. Biv green, yellow, orange, and red. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. The fact that there's 7 of these and 7 of these is a pure coincidence and means nothing. Besides that humans kind of like the number 7. All of these colors of light are all isolated within this one very tiny spectrum in the electromagnetics range, which is called visible light. I see that somebody sent a message in chat. You don't see the whiteboard. Tremendous. All right. Now do you see the whiteboard?
Yes.
Thank you very much for sharing. Perhaps would have been good if I'd known that a bit before, but I appreciate being told. So most energetic, gamma ray, X-ray, ultraviolet, visible, infrared, microwave, radio, clocking in as least energetic. And then for visible light, violet, indigo, blue, green, yellow, orange, red. Red being the least energetic, violet being the most energetic. But all of these colors are all contained within visible light, and the fact that there's 7 of these and 7 of these means absolutely nothing. So don't try to equate violet with gamma ray light, or red with radio light, or yellow with infrared light. These are not valid comparisons. It just so happens that people like 7, is my working theory. Okay, so we covered refraction, and we've talked a little bit about reflection, but now let's explore it in more detail. Reflection is what happens when light is bent in a new direction after hitting a surface, often a mirror, but light can reflect off all kinds of different surfaces. For example, when you walk by an office building and you see the reflection of the sun in the windows, you are seeing a reflection, and the windows are not made out of glass. Now, you can shape a mirror in order to get light to move towards a focal point, the exact same way you can shape glass to get light to move towards a focal point. Only instead of the light traveling through the optical object, it's bouncing off of the optical object. There's very specific rules that govern this, but it's not a class on physics, and so we are going to gloss over them. Let me give you a couple of quick examples of reflection. And pardon me, I seem to have accidentally closed the Firefox window entirely, as I want to do. Nope, there it is. Again, I apologize for the delay. Okay, here's one example of reflection you may have seen before. I just have two mirrors and a candle I can move in between the mirrors, and one of the arms of the mirrors is movable as well. So when I move that arm of the mirror, you get an image of an image of an image of an image of an image. This is one of the powers of reflection, and astronomers make use of this in indirect ways that we will not touch on, but this is super cool to look at, so I give it to you as an example of how reflection works. Another example of how reflection works. Here I've set up two concave mirrors facing each other. At one mirror, I've got a heat source. At the focal point of one mirror, I've got a heat source. At the focal point of another mirror, I've put a match. Let's see what happens if I wait for a bit. And indeed, the match catches on fire. Now, I'm not going to be able to show you the mirror that I mentioned in this slide. It's too bad because it's pretty cool, but we can just go over the basics of this. Well, all right, let me try. Here's the mirror. This side is called concave. So when you have speaking tubes or whispering tubes or whatever they're called, where there's one thing that bends in, and then some distance away, you've got another thing that bends in.
This is a video explaining how to get this experiment set up, the light the match experiment, to get everything lined up in order to be able to light match. So
Pardon me. Ooh, she's got a great mirror. Much nicer than the mirror that I have. All right, back to the screen. So, whispering tubes. Go out in front of the exploratorium. There's one where somebody comes and they put their mouth in an indicated spot and they whisper. Then somebody else, meters away, puts their ear in an indicated spot and they hear the whisper. That's because this kind of mirror can bend energy and put it in a focal point, and it's a real thing. This kind of mirror can't concentrate energy like this. This is a convex mirror. You see these kinds of mirrors in convenience stores or around blind turns because they expand your field of view. You seldom see these kinds of mirrors, but they're interesting to astronomers because you can make energy concentrate in a point. These are the kinds of mirrors that we almost always use. So I'm going to give this a try. It's really not working. Are you getting a sense of a finger coming out towards you?
Yes.
Yeah, this is a much stronger effect when you can hold this and do it yourself. But this is an example of the light that's reflecting off of my finger, going and hitting all around the surface, and then coming back together to form a real thing that I could then analyze because it's physically hanging out there in the air. And that's what astronomers like, to have images physically hanging out there in the air. Because again, what we're going to do with these images right after we get them is just figure out where the image is and stick a magnifying glass on it and then magnify the image. So it's convenient if it's really there. It's not, strictly speaking, necessary. We can work around it if it's not, but it is convenient. So Isaac Newton designed the first reflecting telescope in 1668, and apparently he didn't do this for any reason beyond the fact that when you use two lenses to make an image, you flip the image upside down and that bugs him. When you use a lens and a mirror to make an image, the image is not flipped upside down, and you like that better. However, there's a number of reasons why you might like to use a reflecting telescope that has led this to be the design of telescope that almost everybody uses. So it works basically the same way. You have a concave mirror, and that mirror is going to bend the light towards a focal point. But at some point before the light is completely arrived at the focal point, you use a flat mirror to just bounce the light off of the side of the tube of the telescope. And with the light coming out the side of the telescope like that, you grab your magnifying glass and you move it around until the image is in focus and enlarge, exactly the same way you use a magnifying glass to look at the ink fingerprint left from when you get yourself fingerprinted to work in schools or whatever. This would be another design for a refraction telescope where the light is bounced out at the back as opposed to the side. It really doesn't matter. As long as you collect the light with a concave mirror and then use a flat mirror to bounce the light back out before it reaches the focal point, and then you use a magnifying glass to make the image bigger. This follows the same rules of diameter that I showed you for refracting telescopes. It is the case that the bigger the diameter, the more light it collects, and this relationship goes as an area. If I double the size of the diameter of a telescope, I'm collecting 4 times as much light. If I increase the size of diameter of a telescope by 4 times, I'm collecting 16 times as much light. So on and so forth. It is also much easier to create a big mirror than a big lens. Not only is it easier to create a big mirror than a big lens, but mirrors can be very thin. And they can be arbitrarily thin, really, as long as they aren't so thin that they break apart. And so you can have a tiny little silvering of a mirror on the back of something that's basically as weighty as a piece of cardboard. And you're getting a huge aperture for almost no weight. You can also put the mirror, in fact, you're obliged to put the mirror at the back of a telescope instead of the front of it. And so the telescope is a lot easier to balance. Here is an example of a reflecting telescope. So this uses mirrors as opposed to lenses. And notice that it's quite a bit bigger than that 1 meter diameter telescope I showed you at the Palomar Observatory. And that is how big the mirror is. The biggest refracting telescope in the world has a diameter of 1 meter. This not particularly impressive reflecting telescope has a diameter of 8 meters. It collects 64 times as much light as the largest refracting telescope in the world, and this is not the biggest reflecting telescope in the world. So reflecting really is the way to go, and all major research telescopes use a mirror and a lens, not two mirrors. Here's a schematic of the Gemini telescope, and I'm just going to show you pictures of the telescopes for a while because I think they're pretty. Here's the diameter of the Keck. Now we're getting to a truly big telescope. The Keck is 10 meters in diameter. It's a little bit inconvenient to make a mirror that is that size, so rather than that, they made a whole bunch of hexagonal mirrors and put them together. Now, let's talk angular resolution. Once again, I'm going to go back to the board. Angular resolution is a bit of a non-concept. This is the second reason why you want a big telescope. So in absolute layman's language, the larger your aperture, the more detail you can see. This can be a difficult concept for most people to explore, but there is one thing I'd like to recommend so that you can convince yourself of this. People's eyes dilate when they're exposed to light. Does my otoscope have batteries? Right now, it does not. All right, well, I'll just use a flashlight. So right now I'm in a room. The room is not particularly dark. So my pupil is probably not all that big or all that small. And then I'm going to shine a lot of light into it all of a sudden. Any noticeable change?
Your pupils like dilate.
Your pupils dilate. In the daytime, your pupils are bigger than they are in the nighttime. So human pupil size changes by about 7x. So in the very depths of night, your pupil is...
I think you've got it backwards.
Yeah, in the very depths of night, your pupil is 7 times bigger than it is during the daytime.
Yeah.
So fortunately for this experiment, modern traffic lights are entirely made of a series of LEDs. So your average go light is a bunch of different green LEDs all right next to each other. And I'd like you to try this when you're driving. Pick a spot that you drive by all the time, both during the daytime and at the nighttime, and on a street that you know well. So you can kind of know that you're passing the Walgreens when you're at this point, and you're passing the McDonald's when you're at this point, so on and so forth. I don't want you looking around as you do this experiment unless you're a passenger. You know, driving safety comes first. And see if you can tell that they're individual LEDs and what distance you can tell that they're at. You should be able to notice that there's individual LEDs at night quite a bit before you notice there's individual LEDs during the day. That is because your pupils are much wider at night, and not only are they gathering more light, but you're also seeing finer detail. So having a big aperture serves two different purposes. Purpose number one, you get more light. You gather more photons. You've got a bigger bucket. But purpose number two is it just makes the image sharper. So the bigger we can make our aperture, the sharper the image. Pardon me while I adjust the angle of the camera slightly. All right, there we go. So to me, this is a really cool concept. I would not blame you all at all if you had any questions over it. Any questions? All right, after the obligatory counting to 5, let's return to the presentation. So low resolution is shown above. High resolution is shown below. The main difference between these two things is just that the high resolution image is taken by a telescope with a much bigger aperture than the low resolution telescope. All of a sudden the images become sharper. With the low resolution telescope, it's hard to tell that there's two objects there at all. Indeed, there might be just one. With a high resolution telescope, it's perfectly clear that there are two objects there. And you get that high resolution just by building a bigger telescope. Get that aperture large as possible. That's why big telescopes are important, at least to astronomers. So telescopes with larger apertures have better resolution. And the best resolution a telescope can achieve is called a diffraction limit. Below that is a picture of diffraction happening. You don't have to worry about what diffraction is for this class. I should probably just delete that picture. But the important thing to know about a diffraction limit is that it is a real limit. There's no getting around it. When you see a movie with a spy camera looking down on the Earth, and a person in the FBI says, enhance the image, and the image zooms in a bunch of times, and all of a sudden you can read the license plate on the car, that is fiction. There is no more information in an image that's taken from a picture than there is information that's taken from an image from a picture. If you want to get more information, you need to go up there with a camera with a much bigger aperture and get it. So you can click zoom all you want, but all that happens is the picture becomes grainier and more pixelated. So this is what an image of a star looks like through a telescope. Hard to believe, but true. But 95% of the light is concentrated in that central dot. So usually that's all we see. So astronomical observations begin with the human eye. Again, I think a human pupil goes from about 1 millimeter to about 7 millimeters or something like that. No biologist eye. So it's not a particularly huge aperture. Also, it can only see visible light. So from the point of view of an astronomer, that's not great either. Angular resolution refers to how close 2 points of light can be before we can't tell them apart. And if you want to be able to tell two objects apart, all you can do is build a bigger aperture, get a larger hole that the light is traveling through. The angular resolution of an eye is limited by the size of a pupil. The angular resolution of a telescope is limited by the size of the aperture of the telescope. And towards the end of this presentation, I'll show you something that is truly diffraction limited. A picture that is taken from outer space, and so the only thing that could interfere with the picture is diffraction. Astronomers that are working from ground-based telescopes have a lot more problems than diffraction limits, And in general, those problems are much bigger problems than diffraction is. So, got to deal with that first. But once you put a telescope into outer space where there's no air, all of a sudden your observations are only limited by this weird effective light. And that effective light is called the diffraction limit. So, onwards to the problems of ground-based telescopes. The phrase atmospherical seeing describes how Earth's atmosphere distorts light, and it sets the resolution limits for ground-based telescopes. And in general, that resolution limit is going to be much, much, much more of a problem than the effects of diffraction. So there is the aforementioned mirage as a clear indication of just how much our atmosphere can vary. And that's just over a couple of feet. So imagine how much turbulence there is from the bottom of the atmosphere to the top of the atmosphere. In general, our atmosphere is comprised of different air pockets, and those air pockets all have slightly different densities. Some of them are closer together, some of them are further apart. And the fact that they have different qualities means that each and every little air pocket is going to act like a weird misshapen lens. And because each air pocket is acting like a misshapen lens, the light that ends up arriving at the telescope is going to be bouncing around in all kinds of different directions because it's all arriving at slightly different times and from slightly different angles than the other light that's arriving. Consequently, you get a blurry image of the star that's jumping around all the time because the atmosphere is jumping around all the time. There's a couple of different ways to try to deal with this. None of them work very, very, very well. One thing you can do is just climb as high as you possibly can in as dry an area as you can find. My apologies for butchering this pronunciation. French was my language, not Spanish. Spanish. It's Chile. But Cerro Paranal is a mountain summit 2.7 kilometers above sea level in Chile's Atacama Desert. And a lot of telescopes have been built there recently. That's where the very large telescope is. This photograph shows 4 8-meter telescope buildings, and this is why astronomers prefer very high, very dry sites for their instruments, because the atmosphere is less of a problem if the moisture is low and if there's less of it to see through. So that can partially mitigate the problem. Or you can just use telescopes in space. That eliminates the problem. Astronomers would like all of their telescopes to be in space. That'd be great. But since space telescopes cost at least $1 billion, and sometimes a lot more than $1 billion, that's obviously not going to happen. Or you can use something called adaptive optics. So back to the whiteboard. Adaptive optics is a really interesting thing to consider. It's very, very, very hard to technically achieve. Let me give you a sense of how it's supposed to work. Grab a green laser of a certain wavelength. That's going to make a part of the atmosphere that is very, very, very high up shine. Actually, I think it's a green laser. I've only used adaptive optics in microscope-based technology, so I guess I'm not positive. And also, I can see that I've lost video again, so I will return to you all in a moment. Better? Holler out at me when the whiteboard becomes fuzzy. So, way down here on Earth, got my telescope. And I'm also going to shoot a laser out. And I don't have a working green pen, so I'm going to use an orange pen. And somewhere way up here in the atmosphere will shine. Now, I know what this should look like. I made that laser. I shot it upwards, so I know what the fluorescing atmosphere should basically look like. But then I look at that laser using the shining coming from the laser, using my telescope, and I make sure that part of that field of view is a star that I actually care about. Shown here much, much, much closer than it actually is, at least hopefully. So because I know what the sky shining due to the laser should look like, I take my telescope and I pass the light from the telescope through a mirror that can physically deform. I make the mirror go like this. And I make the mirror contort itself into a shape such that this shining level of the upper atmosphere looks like it actually should. And then with all the light contorted from making this look like what it should, ideally the star will also look like what it should because this is on top of most of the atmosphere. That's adaptive optics. Now, this is tremendously difficult to put into practice, but that's the basic game plan. Questions about adaptive optics? Okay. I don't want that. So the light comes in from the telescope. It hits the mirror that distorts its shape. And then hopefully the image of the star is corrected. And so we go from an image of the star with no adaptive optics used, which is clearly junk. Then you introduce the adaptive optics, and the star shows up pretty cleanly. Here is a picture of Jupiter taken with a ground-based telescope. Notice the detail. You don't get Jupiter to look like this if you point your telescope upwards and just look at Jupiter. Doesn't matter how big your telescope is, it's going to be blurry due to the effects of the atmosphere. But with adaptive optics, you can, in theory, remove that blurry effect from the atmosphere. And here is a telescope just pointed at the center of the galaxy. Adaptive optics are off. Let's turn them on. There. So this is the power of adaptive optics if it works. And there's serious technical challenges associated with it, but nonetheless, astronomers work hard on solving them, and often it does work. By the way, quick side note, I've been told by people who work on adaptive optics that these lasers are enormously loud and terrifying because they rip the air apart as they fire upwards. The moment they turn on, they just fill the entire observatory with blinding light, and it's really scary to be near them. So take that information under advisement before you plan your tour of telescopes. All right, now we go to review, and I'm going to give you 2.5 minutes to work at this. What time is a half-full waxing moon directly overhead? Just draw a picture and figure it out. So I'm not asking you what time does it rise or what time does it set. I'm asking you what time is it directly overhead. I'll see you in 2 minutes and 30 seconds, and as always, feel free to ask me any questions. Or private chat me messages. Yeah, I'll just stop sharing for a minute because I can't get to the private. Okay. People are not asking me questions, they're just sharing what they think their answer is. Okay, anybody need some more time? A range of answers. All right, well, that's what makes teaching exciting. Let me try to solve the problem myself, and then we'll see how I did it differently than you. So I tend to, oh wait, sorry. Let's get to the whiteboard. So I always start this way. This is a full moon, this is a new moon. I know the moon goes around the earth counterclockwise, so this way it's waxing. This way it's waning. And I don't actually remember. Was it a waning half moon or a waxing half moon?
Waxing.
It was waxing. All right, that puts the moon right here. And that means it is directly overhead when the earth is turning from the dark side into the light side. And so the moon is directly overhead right at sunrise. I don't know if anybody started the quiz and is flicking through as we go, but trust me, this is exactly the kind of question that I'm likely to ask on a quiz. So anybody want to ask any follow-up questions or ask for clarifications or even ask for me to work through this class of problems and give a few more examples? You can also send me a private chat if you don't want to turn your mic on and say so. Just hit me with a period enter so I know something's coming. All right, moving right along. So the answer is B, dawn. At least it's dawn if I did it right. Did I do it wrong? Nobody's telling me I did it wrong, so I guess I'll assume I did it right. Everything that's been said at this point, where would you want to put an observatory? You want it to be dark if it's an optical observatory. If it's a radio observatory, you want it to be far away from cell phones, which can have real consequences. There's a part of, I believe, South Carolina where people are forbidden from using cell phones or having radio antennas or receiving radio transmissions or anything like that because there's a radio telescope hanging out there that's so sensitive. But is that worth it? Because the technological growth of people living in that circle circumscribed around the radio telescope is really diminished. Like imagine being told you can't use a cell phone because you're too close to a radio antenna. So you want to be away from light pollution. Using a radio telescope, you want to be away from radio transmissions. So that's everything from cell phones to 91.5 KXCM playing the greatest oldie hits of the 70s and 80s. All of that radio stuff can mess up a radio transmission. You want to be dry. Water vapor blurs images, blocks infrared light, and gets telescopes covered with unwanted residue. I believe that means rain. You want to be high. The higher you can put your telescope, the less atmosphere there is to distort the images. And you want it to be near the equator so you can see more of the available sky. Remember, right at the equator is the only place where you can see every single star. The North Pole is dead on the horizon when you look north. Or the North Star is dead on the horizon when you look north. The South Star, were it to exist right now, which it doesn't, we're going to have to wait another 8,000 years or so to get a new one. But the South Star would be dead on the horizon at the South Pole. And so in theory, if you hang out at the equator, you would see every star over the course of a year as you move from one side of the sun to the other. But the thing about the equator is it turns out to have a lot of monsoons and tropical weather. So that's not great for telescopes. And so they tend to be not too close to the equator, but as close as they can get away with within the bounds of rainy weather. Now, how do astronomers take pictures? Well, since the very beginning of astronomy in combination with paper, people have just drawn images of stars. And if you've got great eyes and a steady hand, that works okay. But it's not ideal. Photographic plates would be the next step up. The nice thing about photographic plates is you can point your telescope at something, and then you can just leave the photographic plate beneath it. The more light that goes through the photographic plate, the more exposed the photographic plate becomes. And if you let it run for long enough, this lets you see stars that aren't even visible in the telescope through the human eye, just because those spots on the film are exposed to enough photons eventually that the star starts to show up. So photographic plates are a big step up. But they're not what we use today, for sure. Here's the first photograph of the moon. What we use today is something called charge-coupled devices. Look at your cell phone. The back and the front of your cell phone probably have a CCD in it, a charge-coupled device. The front of your cell phone is for taking selfies, and the back of your cell phone is for taking pictures of other people, which I believe is called reverse selfies. But the technology that drives these cameras was developed by astronomers. We wanted to be able to create something that could digitize information received in the form of light. And for this, the inventors of the CCD won the Nobel Prize in 2009. Now, CCDs are better than photographic plates. Not only can we cram these things closer together than photographic plates are sensitive to, but they also automatically generate digital data, and then you can send that data all over the world. At the beginning of the use of CCDs, we were sending the data all over the world on big old reels of magnetic tape. Nowadays, you just fire it off over the internet. But whatever, it can be encoded and saved for forever with theoretically perfect accuracy. This large CCD, which is very large, is about 6 inches across and has the thickness of a human hair. So that's really sensitive. I mean, that's bigger than your cell phone, and your cell phone has only a tiny proportion of its body taken up by a CCD. So you can imagine that it would be a lot more sensitive. And here's what you can see in a star field using a photographic plate, presumably left there to be exposed for a while. To the left and to the right is what you can see of that star field using a charge coupled device, or a CCD. And it's a lot better. So now everybody uses CCDs, including you, when you take pictures with your camera. And so around the 1980s, they became the main tool that astronomers use. And that has continued right up to this present day. Now, spectrograph. I can't give you diffraction gratings anymore, which makes me angry, but whatever. A diffraction grating is something that semi-magically takes white light and splits it into a rainbow. And they really work. They can be both transmitting diffraction gratings, which is the kind that I would give you, or you can build a surface that reflects light off of it and causes the rainbow spread. And astronomers want to do this because of spectroscopy. They're looking for those absorption lines, they're looking for those emission lines. They're keys as to what the chemical composition of a star is, how fast it's moving towards or away from us, so on and so forth. So refraction grating will split light exactly like a prism, only instead of splitting it one way, it splits it two ways, so that's a little handier. But it's not the only wavelength you want to work with, right? Infrared light is super handy, and the atmosphere is extremely good at blocking infrared light. But infrared light can pass through lots of objects that are blocked by visible light. And there's lots of wavelengths we'd like to be able to see from the planet Earth, and we can't. Gamma rays, X-rays, most ultraviolet light, most microwave light, all of that is completely invisible from the surface of the planet. In some cases, thank goodness. I mean, we do not want gamma rays raining down on the surface of the planet. We do not want X-rays raining down on the surface of the planet. But the subtraction of microwave light is just inconvenient, because microwave light doesn't really hurt anybody excepting for that one very thin wavelength of microwave light that will make water agitate around. So we went over what magnitude was last class, but let's do a couple of activities to make sure that it really took. Activity number 1. Rank the distance from greatest to least that each car is from you. So chat me the answer. Great. People are getting it right. Tremendous. Now, so A is the closest, then D, then C, then B. Good on you. Now, remembering that to an astronomer, brightness means how much light is received by your eye, not how bright the object initially was. Assume all these headlights have the same intrinsic brightness. Have the same intrinsic luminosity. They're all putting out the same amount of total light. And then put the brightness of the cars in order from most bright to least bright. And also pretend that car C is coming towards you, even though it really shouldn't be. So B, C, D, and A are all coming towards you. Then send me a chat telling me what you think the answer is. Which is brightest, which is the second most bright, which is the third most bright, which is the fourth most bright, in this instance also known as the dimmest. All right, well, this time I'm not getting any answers at all, which is a little disturbing. I'm not sure if I've lost audio or if y'all are thinking it over. Let's say that if you're going to give me an answer, do so in the next 30 seconds. Okay, this is interesting because I have gotten absolutely zero responses, and I'm surprised by that given the nature of this question. If anybody's got a mic hanging around, can you tell me if you sent a response?
I sent you one.
Okay, so something else is going on. All right, well, A is the brightest, D is the second brightest, C is the third brightest, and B is the fourth brightest, otherwise known as the dimmest. And then the luminosity of each of the headlights is the same. So let's try this again, maybe because wait, that's not the one I want. Okay, so another activity that seems to me to be pretty simple. The figure below shows 5 stars as they appear in the night sky from Earth. A darker shading indicates the appearance of a dimmer star. Note that star B is the darkest. So rank the brightness of each star as it appears in the night sky. Oh, now I'm getting chats. Ah, sorry. All right, I'm getting chats, but I can't seem to actually open the chats. So, given that nothing else is broken, I'm not going to say this is a big enough technical issue that we should reboot the Zoom or whatever. So from brightest to least bright, we've got A, E, C, D, B. And finally, I'm going to touch on this. It's never going to be graded in this class. Actually, I'm just going to turn this off and highlight the screen for a second. So I'm never going to grade this. I'm never going to hold you accountable for it because it is a total accident of history, and I think it's the opposite of the way things should be. But I feel like I should note it as well. The way that astronomers classify the brightness of stars is that the lower the number, the brighter the object. So something that has a brightness of 7 would be dimmer than something that has a brightness of 2. Something that has a brightness of 2 is dimmer than something that has a brightness of -3. That's how the system's set up, and it's not going to change just because I don't like it, but it seems quite a bit opposite of what one would intuitively do. So returning to this slide, when you consider how bright a star is in the sky, C would be brightest, then D, then E, then A, then B. And if you're curious how much brighter, unless I'm misremembering it, turns out that a human eye is sensitive to a change of brightness of about 2.5. So something that has an apparent magnitude of 1 is 2.5 times brighter than something that has an apparent magnitude of 2. Again, I will never test you over this. I'm just providing the information for those who might be curious. So that is how astronomers measure brightness. That is the metric that we apply for whether something is brighter or less bright, is that we count brighter objects as having a lower number. That's just how it is. Nobody asked me. So this is a sense of what you can see from different wavelengths of light. Here is a radial image. That tiny little thing in the middle is a galaxy. This galaxy has a few 100 million years ago had a meal. The central black hole ate something. And when it ate something, it generated tremendous shock waves to its top and bottom. And we can see those shock waves extending out into intergalactic space using radio telescopes. This was a tremendously violent event, but it happened so long ago that the shock wave is no longer emitting visible light. It's no longer emitting microwave light. Shock wave is only visible in radio light by this point. So as you might expect, we use radio light to analyze things that are kind of low energy or things that are kind of high energy, because something that's hot enough to emit visible light is also hot enough to emit an awful lot of radio light. But if you're looking at something that's very low energy, low enough energy that it's only putting out radio light, then you're out of luck. You've got to look in radio light. It's the only way that the object is emitting light at all. And there's an awful lot of things in the universe that astronomers are curious about that have that low of a temperature by this point. Here's more pretty pictures of telescopes. Here's a radio telescope. I believe this is the one that requires citizens and visitors to the United States to not use cell phones or have radio stations anywhere even remotely near it. Here is a submillimeter array, which is a fancy word for kind of high energy microwave light. And they put it as high and as dry as it possibly can. And it still only kind of works. But something that kind of works is better than something that doesn't work at all. And also a cool picture of the Milky Way in the background. Here is something called the Very Large Baseline Array, which is a bunch of radio telescopes all over the place. And by this point, I'm going to stop and pause another thing that I won't grade you over, but I'm going to talk about because I think it's real cool. If you have two radio telescopes, radio telescope here, radio telescope here, then the distance in between them acts as the aperture for the purposes of resolution. Now, they aren't acquiring that much light. The amount of light they acquire is just this plus this squared. But for resolution purposes, it matters only how far away they are from each other, and so they can be really far away. So for light gathering purposes, the physical size of the radio telescopes is the things that matter. But for resolution purposes, the distance in between the radio telescopes is the things that matter. Now, as y'all were scrolling through Facebook or Twitter or whatever it is that young people use, did you see that picture of the black hole? Well, in that case, your Twitter feed's a lot different than my Twitter feed. I saw a picture of a black hole. Or more accurately, I saw a picture of a shadow of a black hole. You can't actually see a black hole, but you can perceive its effects based on what it's doing around it. And the way they made that image is they used every radio telescope on Earth. And so they basically made a telescope that, for the purposes of resolution, has a diameter of the entire Earth. And they did this a while ago, but it took like half a decade to actually correlate all the data and make it so telescope A was talking right to telescope Q, was talking right to telescope D, so on and so forth. We tried to do the same thing to the black hole at the center of our galaxy, but that data is still being disentangled. But maybe someday it will actually be put into a form that's useful, and you'll see a picture of the shadow of the black hole at the center of the Milky Way. Here's the largest radio dish in the world. Last I heard, it was broken, and then I guess they fixed it, and then it broke again. And this time, I think for good, because part of the dish has collapsed. This is Arecibo, and it was kind of unique in that it could both look at radio signals and send out radar pulses. It's a Cold War artifact. The military wanted to build something that could precisely determine how far away other objects were, especially satellites. And so Arecibo was capable of doing a kind of echolocation using radio waves. It would shoot out some radio light. The radio light would hit the satellite or the moon or whatever, and a portion of that light would bounce back to Arecibo, and you'd see how long it took, and bingo, you had a very, very, very accurate measurement of how far away something was. This is the only large-scale telescope that works this way, so now that it's broken, we don't have one that does this, as far as I know. I'm sure the U.S. military has something similar kicking around somewhere along with China and perhaps Russia. I don't know. Russia's pretty broke right now. Other things you can do is to just put a telescope on top of an airplane and fly it real high. Judging by the size, this is a microwave telescope, and it is literally floating upwards on a wing to try to get a little bit of data as high as that plane can possibly take it in the atmosphere. Now, back to infrared, which is the real gold standard of the wavelength that astronomers would most like to get at for a whole bunch of reasons. This is a star cluster called the Pleiades, my favorite star cluster, in infrared light, in visible light. When you look at it in infrared, boom. Infrared light sees right through all that dust and enables us to observe the stellar nursery with a lot more detail. Same thing with all this dust near Orion. So the sword of Orion is a huge star-forming region, but it's covered with dust, like star-forming regions usually are. And so if you can see it in infrared, you can see all that star formation going on. You can see the little stars lighting up and starting to form. But if you're stuck with visible, there's no way to know what's actually happening because it's all completely obscured. Questions or back to the presentation? All right, so every wavelength is important, but for a bunch of reasons that we'll learn throughout the class, infrared wavelength is probably the most important of all. Now let's talk about what you can get if an image is truly diffraction limited. It's a famous picture. It's a whole bunch of galaxies. If you were to imagine how big this picture is, take a grain of sand, if you can find a grain of sand in your house, and hold it up at arm's length. The size of this picture is how much of the sky is covered by that grain of sand being held at arm's length. So only two of the objects in this picture are stars. They're both very blurry and out of focus because the Hubble wasn't trying to focus on stars, it was trying to focus on incredibly distant galaxies. So count how many galaxies there are in that picture, and then imagine how many grains of sand held at arm's length it would take to completely encircle your head. Then multiply the two numbers together. This is basically how astronomers arrived at the conclusion that there's around 100 billion galaxies in the visible universe. So a lot of galaxies out there. And this is also an image that can never be seen from an Earth-based observatory. Adaptive optics or no, there's no way to get an image that clear if the atmosphere is in your way, not at something that distant. And so the Hubble Space Telescope really has let us see things that we could not see any other way. Here's a picture of our X-ray telescope. Here's a picture of our replacement infrared telescope, which has been in development for a couple of decades going on now and has never been launched. When it's finally launched, it's going to go to the far side of the moon, where we couldn't possibly replace it. And here's the thing about the James Webb. It has over 100 distinct points of failure on it. Like, those mirrors are meant to unfurl and point in the right way, and there's tons of actuators that have to do exactly the right thing, or else it's not going to work. But in any normal spacecraft, you don't even want one point of failure. You want many, many, many redundant systems so that if something fails, something else can immediately take over. So I don't have a lot of hope for the James Webb, but if it gets up and it works, it'll be tremendously valuable. One of the ways that infrared light is so important is that, as you recall, when objects go away from us, they get redshifted. And the further away an object is from us, in general, the faster it's going away from us. So the most distant galaxies we can see are so redshifted that their visible light, the light that stars naturally tend to glow in, has become infrared light. And we can't see them without an infrared telescope. This is the main reason that astronomers salivate over the prospect of having an infrared telescope, is that it would enable us to see visible light from things that are so far away that the visible light has transformed itself into infrared light because of redshifting. Here's what the extremely large telescope will look like if and when it finally gets built. It's got a mirror that is about 40 meters across. Astronomers are obviously good at naming things. There's the very large telescope, the extremely large telescope. Presumably at some point we'll get the ginormously large telescope. So that's what telescopes look like in general. We also send out probes. Here's Voyager. Voyager 1 and Voyager 2 were kind of launched at exactly the perfect moment. Voyager 1 went by Jupiter and Saturn and continued to just head out of the solar system. Eventually, it encountered the shock wave when the energy pushing outward from the sun finally gives out, and you are in true interstellar space. Voyager 2 was even luckier. It launched at a time where it could hit Jupiter, then Saturn, then Uranus, and then Neptune. And it's also the only probe that's ever gone by Uranus and Neptune. You know, we sent a probe to Pluto recently, but never another probe to Uranus or Neptune. And so New Horizons went to Pluto recently as July 2015. And this is what it saw. There's Pluto, there's Charon, Pluto's moon. Pluto, of course, no longer a planet, mainly because it doesn't have enough gravity to clear the area of its orbit. It's surrounded by lots and lots and lots of other things that are pretty Pluto-like. And also because we found objects that are as big as Pluto and objects that are as massive as Pluto, give or take. And what were we going to do? Make all of those things planets? If we did, we'd be up to 15 planets right now. And finally, no one in the International Astronomical Union went out and said it, but if you took Pluto out to about Earth's orbit, Pluto would just melt. And it seems like you shouldn't call something a planet if it would just melt if it got a little closer to the sun. But there's really no difference between what Pluto's made out of and what your typical comet is made out of. Pluto's just a whole bunch of comets that have coalesced together to form a single object. And finally, we send rovers. Here's 3 generations worth of Mars rovers. If I were to put this slide together today, I would need another thing in it to represent Perseverance, which is our new rover on the planet. Curiosity took a picture of Mars, the best selfie in the world because its camera arm is long enough to capture a picture of itself. So this is how we discover what Mars looks like. Notice that these rovers tend to cover the same area over and over and over again. Look at the tracks from the tires. They don't move around fast, and they tend to spend a lot of time looking in intense detail at things in their immediate environment. Because eventually the wheels break, and you want to get the most you can out of any one site before you move it forward as you work towards that inevitable point where all four wheels are broken. And every once in a while, haven't done it in a long time, we go someplace and we come back. So that looks like this.
You're looking at one of the most incredible moments in human history. That's Neil Armstrong and Buzz Aldrin walking on the moon. Okay, maybe you've seen this clip before, but think about that for a second. They're on the moon, a celestial object nearly 240,000 miles into outer space. That distance is like flying all the way around the Earth 9.5 times. Millions of people around the world watched on July 16, 1969, as Apollo 11, carrying astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins, launched from Cape Kennedy, Florida, and disappeared into the sky. It was the climax of years of preparation and research, and the pinnacle moment of the so-called space race between the United States and Soviet Union, a years-long rivalry to compete for dominance in space exploration. For the 8 days following the launch, the world awaited the return of the would-be heroes. So what actually happened between here and here? So let's start with the components of the ship that were discarded one by one until this became this. Here's the rocket that sent the astronauts into space, the Saturn V. The three stages of the Saturn V each played a different role in launching Apollo on a path to the moon. We'll get to that later. On top of the rocket is the actual Apollo spacecraft. It's made up of three parts too. There's the lunar module, the component that would eventually land on the lunar surface, the service module, which had propulsion systems for course corrections and entering and escaping orbit, and the command module, where our three heroes were for most of the mission. And last but not least, this is the launch escape system, which was designed to pull the command module away from the rocket if something went wrong during launch. Together, all these pieces made up the Saturn V rocket and Apollo 11 spacecraft, but it's the way they came apart that made the moon landing happen. The Saturn V's first stage launched Apollo, carrying the spacecraft 42 miles above the Earth and reaching a speed of about 6,000 miles per hour. The first stage then detached, and once the Saturn V's second stage kicked in, the now needless launch escape system jettisoned too. The second stage propelled the spacecraft even farther and faster into space, and after it detached, the third stage of the rocket fired briefly to knock Apollo into a parking orbit, 103 miles above the Earth's surface. Here, final checks were made, and the Saturn V fired again to set Apollo on course to the moon, in a move called the translunar injection. Once the spacecraft propelled away from Earth, the Saturn V's job was done. Now, the astronauts needed to pull off a mid-flight maneuver to reconfigure the ship so the crew could access the lunar module, which had been stored in a protected compartment during launch. To do this, the command service module detached and flipped 180 degrees, docking with the lunar module and extracting it. In the process, they ditched the third, now useless stage of the Saturn rocket. This whole high-stakes launch process only took about 3.5 hours, and this, the completed Apollo spacecraft, was the end result. For the next 3 days, Apollo coasted through space, until it finally reached its target and was pulled into orbit by the moon's gravity. This is where the crew split up. Armstrong and Aldrin transferred to the lunar module, named Eagle, and slowly descended toward the surface, while Collins continued to circle the moon in the command module, called Columbia. Now, here comes another tricky part, landing on the moon. To make this historic moment happen, Eagle turned and used its engine to slow its momentum and ultimately touch down on the lunar surface.
The Eagle has landed.
The moonwalk was broadcast live on television, immortalizing Neil Armstrong's words here.
That's one small step for man, one giant leap for mankind.
I think that was Neil's quote. I didn't understand it.
No, one small step for man, but I didn't get the second phrase.
After about 21.5 hours on the moon, Eagle performed the first launch from a celestial body that wasn't Earth, leaving its landing gear behind and timing its ascent with Columbia's path in lunar orbit to rejoin the spacecraft. Once Armstrong and Aldrin transferred back into the command module, the lunar module was no longer needed. Just like before, Apollo needed to break out of orbit. This maneuver was called the trans-Earth injection, and began the 2.5-day journey home. Upon approaching its entry point into Earth's atmosphere and no longer needing its propulsion engines, Apollo jettisoned the service module and prepared for re-entry, protected by the now exposed heat shield on the bottom of the command module.
Apollo blazes across the heavens, coming back to Earth at 25,000 miles an hour.
Parachutes deployed, and Columbia splashed down safely into the Pacific Ocean. And what was once a 3,000-ton behemoth of rocket, fuel, and freight was reduced to this: a small command module floating in the ocean, carrying 3 astronauts and rock samples collected from the surface of the moon.
And that's how we know that the moon is Earth's crust, because we have rocks from the moon that we can identify. And incidentally, they're talking about how far away the moon is. I'm kind of amazed at how close it is. It takes 2 years at minimum at closest approach to get to Mars. Contrast that with how long it takes to get to the moon. It's next door. I don't understand why anybody would want to go to Mars before we go to the moon a bunch of times. And so every once in a while we have sample return missions. It's been, what, 30 years, 40 years? Nope. 1972, 1, 2, 3, 4, 5, 50 years. Almost 50 years since we did it last. Line of the day, Venus. What can I say about Venus? Venus is awful. It's the hottest planet in the solar system. It rains sulfuric acid there. The atmosphere is so thick it would crush a submarine's hull, no problem. And that's why it's the hottest planet in the solar system, because it's got a thick atmosphere, and that atmosphere makes the greenhouse effect extremely effective. Venus is hotter than Mercury. And unlike Mercury, there's no deep chasms where the sun doesn't touch, and so little pockets of ice can hang out. The entire planet is boilingly hot. The cloud cover is extremely reflective. It reflects more light than any other planet in the solar system. And the planet itself turns so slowly that you could walk, not very fast, and keep the sun directly overhead for forever. Of course, when I say you, I don't mean you. I mean some creature that could survive on Venus, which is very difficult to imagine. It also spins upside down relative to every other planet in the solar system, so you need to walk east, not west, to keep the sun above you. And it probably does that because of some kind of early solar system collision. All the water has been removed because the magnetic field is so weak. Basically the same reason that all of Mars's surface water was removed. Mars still has a ton of water left beneath the surface, but if the water was able to mix with the air and get up into the air, then it was taken away by the solar wind. Because the water is gone, Venus can't have plate tectonics anymore. Not a problem for Mars, which no longer has any heat in its core, we think, but a big problem for Venus, which is still very hot on the inside. Because Venus's plates can't move around and dissipate that heat, the way the heat does get dissipated is that it just builds up and builds up and builds up, and every few 100 million years the entire crust turns into molten lava. And then that dissipates the heat, and you got an entirely new crust. That's why Venus really doesn't have any features. No craters, very few mountains. It's pretty darn flat in comparison to a planet like Mars or Earth. For some reason, the the United Soviet Socialist Republics kept throwing probes at Venus until some finally survived and were able to reach the ground. The initial probes had parachutes that opened, and Venus's atmosphere was so thick that they didn't reach the ground before they melted. But finally, they figured out the right size parachute and a strong enough capsule that it touched down, and it worked for a glorious couple of minutes. And because Venus's atmosphere is still transparent to radio light, it was able to send back some pictures. And there it is. The surface of Venus, the worst place in the entire solar system. And that's it. That's the end of the class. Done almost an hour early. You're welcome. Anybody got any questions?
Will we be having class next week due to spring break or?
No, and that means I should change the due date of this next assignment from being on the 30th to being on whatever the 30th plus 7 going into the next month is. Now, the assignment for Unit 5 is still going to be due on the 30th, but I'll make the assignment for Unit 6 due on April 6th. So that's the day after we have class again.
And where do we X the test?
The quiz?
Yeah.
Open up your canvas right now. It should just be there, mixed in with the assignments. Take a look. I'll switch to student view real quick and see where I see it. Upcoming assignments. Quiz 1, Unit 1 through 3. Available until March 25th at 11:59 p.m. Due March 25th at 11:59 p.m. with 20 points. So I see it. Please message me if you don't see it. Shoot me an email. Any other questions? Are you sure? Because once I log off, I'm going to be harder to get a hold of. All right, then I'll leave it here for today, and I'll see you in 2 weeks. Unit 5 homework is due in a week and a day. Unit 6 homework will be due in 2 weeks and a day. And you got a quiz, and right now that's all I know. So shoot me a message if there's any kind of technical problems. Ciao.